going to illustrate the difference between mass, weight, apparent weight, and g-force so that you don't confuse these four closely related things. First of all, the mass of an object measured in kilograms, that depends on how many and what kind of atoms are in the object. And the important thing is that mass does not change from place to place in the universe unless you add or remove atoms from the object. Let's contrast that with weight. By the weight of an object, we mean the magnitude of the force of gravity acting on that object. So weight is a force measured in newtons. Magnitude of force of gravity, sometimes we just call it a capital W for weight. It also is then represented by m times little g here, g, the strength of the gravitational field. And the weight of an object therefore changes when you move the object to a location where the gravitational field is stronger or weaker. As with our sheep here that we took from the planet Earth to Mars, the mass of the sheep stayed the same number and type of atoms in the sheep, but its weight went down when it went to Mars because the gravitational field on Mars is weaker than it is on Earth. Therefore, the force of gravity on Mars is weaker than the force of gravity on Earth, and weight means the magnitude of the force of gravity. You probably measure your weight in pounds, which is the English engineering or British imperial unit for force. Pound force is the unit that's used in those systems, or sometimes just called pounds, lb for short. lb stands for Libra. So you can convert newtons to pounds like so, and pounds back to newtons. But what you can't do is convert kilograms directly to pounds. This is because kilograms is a measure of mass and pounds is a measure of weight or force. But if you specify a little g, the strength of the gravitational field, by specifying where you are in the universe, then you can calculate the weight in newtons of an object of mass m using Newton's law of gravity here. The weight equals m times little g. And then you could convert the weight in newtons to weight in pounds if you wanted. So, for instance here, on the surface of the Earth, where little g, the strength of the gravitational field, has value 9.8 newtons per kilogram, a 1 kilogram object, like this piece of brass right here, that's a 1 kilogram piece of brass, that experiences a gravitational force with a strength of 9.8 newtons, or about 10 newtons. 1 kilogram times 9.8 newtons per kilogram is about 9.8 newtons, or about 10 newtons of force. So this kilogram weighs about 10 newtons, which is equivalent to about 2 pounds. Here we have half a kilogram. Half a kilogram right there has a weight of about 4 newtons, or 1 pound. This is about a pound of brass right here. It has a mass of half a kilogram. And then here, this is a tenth of a kilogram, 0.1 kilograms right there. That has a weight of about 1 newton, or about 0.2 pounds. So for comparison, we've got 3 pieces of brass. This one weighs 1 newton, this one weighs 1 pound, and this one has a mass of about 1 kilogram. That brings us to apparent weight, number 3. The thing is, you don't actually feel the force of gravity pulling on you. Astronauts in orbit are described as being weightless, even though the force of gravity is pulling on them. And so, by definition, their weight, the force of gravity is pulling on them, and that force of gravity is not that much different than it is down on the surface. Their weight is not that much different than it is down on the surface. Nevertheless, we say that they are feeling weightless. You feel weightless when there are no forces other than gravity pushing or pulling on you. Weightless means the same thing as free fall, in free fall. So this astronaut is in free fall, feeling weightless. And so is, back down here on Earth, this wrench that's been dropped off of this work table here. This wrench falling towards the ground, only the force of gravity is significant acting on it. This wrench is weightless, it's in free fall. This wrench doesn't feel like it weighs anything right now, just as this astronaut doesn't. So for both of these objects, their apparent weight is 0, although their actual weight is not 0. There is a force of gravity here and here, so they both have a weight at this time, but they feel weightless because their apparent weight is 0. So apparent weight, that's how heavy you feel. We need another concept to capture the difference between forces you feel and gravity, the one force you don't feel. So we call this concept the apparent weight. Your apparent weight at any given time is the magnitude of the net force from all other interactions except gravity. The net ng non-gravitational force acting on you. So contact forces and forces from the air and pretty much every force that pushes you around all day other than gravity contribute to your apparent weight and make you feel heavier or lighter. So some examples. Say you're standing still in a room, and then the only non-gravitational force acting on you will be the contact force from the floor. The magnitude of that contact force is your apparent weight. How heavy you feel. Since it will be equal to the magnitude of the force of gravity, aka your weight, as you stand there in static equilibrium, your apparent weight under these circumstances will be equal to your actual weight, and you will feel normal. But if, on the other hand, a trap door opens up and that contact force with the floor vanishes and you enter free fall, then the net non-gravitational force on you will be 0. There are no non-gravitational forces acting. And therefore, your apparent weight will be 0 as you fall. So when we say that someone is in a state of weightlessness, what we actually mean is that their apparent weight is 0. Suppose then that you land safely on this platform here, which then begins to push you back upwards, like this pneumatic platform here pushing you back up. In fact, accelerating you back upwards. Here, the normal force from the platform, that is going to be our apparent weight. This has to be greater than the force of gravity so that the net force is upwards to accelerate you upwards. So here, if the normal force, your apparent weight, is greater than the force of gravity, your weight, then you are going to feel heavy. Your body feels heavier than usual because you're being pushed with a non-gravitational force that's greater than your weight. Let's see. Apparent weight is often expressed as g-force. That brings us to number 4, g-force. G-force is a dimensionless ratio, so it doesn't have a unit. We just measure it in G's. And if your apparent weight is equal to your ordinary weight, you feel normal and are said to be experiencing 1 G. To convert your apparent weight to G's, G-force, to convert to G's, just divide your apparent weight, the net non-gravitational force, that magnitude, by your ordinary weight on the surface of the Earth. So you would use 9.8 newtons per kilogram for little g right here, the ordinary value of little g near the surface of the Earth. That ratio is what we call the g-force. So let's use that to compare. Let's use this concept of g-force to look at those 3 scenarios from before. Okay, here, so if you're standing still on a surface and your apparent weight is equal to your weight, then the ratio of the two is 1, so we say you're experiencing 1 G. In other words, you're in equilibrium here, and you feel normal. So normally, you walk around throughout your day experiencing 1 G. Note that then your acceleration is 0. That's equilibrium. If, on the other hand, you are in this state of free fall, Whether your apparent weight is 0, then this ratio of apparent weight to weight is 0. So the g-force here is 0 g's. Free fall means you're in 0 g's, feeling weightless, but note that you are accelerating. The force of gravity is still there. The weight, you still have a weight, so you're still accelerating, but you don't feel it. You're in 0 g, you're feeling weightless. That's free fall. And then here on that platform, accelerating upwards, let's say the apparent weight here was double in magnitude, your actual weight, then this ratio here would be 2, and you'd be experiencing 2 g's. And if you're feeling 2 g's, you're feeling twice as heavy as you normally do. So a 150-pound person would feel like they weighed 300 pounds under these circumstances as the platform is accelerating them upwards. Note that you are accelerating here. Okay, a couple remarks about g-force. G-force is not the same thing as acceleration. The g-force is acting on you. That's not your acceleration, as we saw in the examples. And g-force, despite its name, is not a force. It's a terribly named thing. Sorry about that. G-force is not a force. It's a dimensionless ratio of two forces. It's best described as your relative apparent weight. Relative meaning this ratio. G-force acting on you is your relative apparent weight at that time. So for comparison, consider the Apollo space program, which took U.S. astronauts to the moon in the 1960s and 1970s. On launch, a Saturn V rocket on liftoff would exert about 4 Gs on the astronauts up here in the command module. The astronauts felt 4 times heavier than their normal weight on liftoff. But even more extreme was on reentry. This little command module up here, that little tip, is all that returns to the Earth. This re-enters the atmosphere, splashes down in the ocean, and upon reentry, our astronauts experienced about 6.5 Gs of G-force. That's intense. Imagine trying to lift your arm to push a button in the module here when your body feels like it weighs 1,000 pounds.